VP of Engineering for Quadrant Solutions. We're going to talk about some soft magnetic materials and their uses. Soft magnetic materials are used as a magnetic conductive material. Much like you use copper or aluminum to conduct electrical current, we use soft magnetic materials to conduct flux. They have very low reluctance. It's the electrical equivalent of resistance, so they allow us to put a lot more flux density in a small area than air or other magnetically conductive materials do. They have a very high permeability, which lets us use different properties of the material to change magnetic circuits. So soft magnetic materials is a broad term. Even most hard magnets, permanent magnets, are soft magnets as well. There's not a good guide to tell us what's in between those two. They're just really bad soft magnets. So the permeability of sintered NdFeB, a typical neomagnet, is about 1.05. The permeability of steel is in the range of 10,000, so it's a big difference. But you can conduct flux with sintered NdFeB, just not as much. It's not much better than air is for the circuit. So when we're designing a magnetic circuit, we want to design the whole circuit as one piece. We want that flux to flow from the magnet, which is essentially your power source, your battery. We want that to flow from the magnet, from the north pole to the south pole, just like you would the positive pole or the positive terminal to the negative terminal of a battery. And we need something for that to go through. Now, unlike electricity, air is conductive. So our flux is perfectly happy to flower out from the north pole and go to the south pole around the magnet. But we can steer that with a soft magnetic material, something with a lower reluctance, inversely a higher permeability, can conduct that flux and draw it in that direction. So if we put steel around the magnet will not only perform better, but we can direct the flux where we want it. If we put steel somewhere behind a sensor, we can draw flux that direction. Some of the soft magnetic materials we work with are stainless steel 400. It's 430, 416. We have stainless 17-4pH, which is a little mechanically harder, but has similar magnetic properties to a 400 series stainless. We've got 1010 or 1018, 1008 low carbon steels. We've got iron cobalt that can be mixed in different quantities of cobalt and iron for different properties or mechanical properties. We also have different ceramic materials that we can use. And then we have amorphous iron materials such as iron nickel alloys. We can get amorphous sheets and nanocrystalline materials if it's grown the right direction, if the crystal structure is grown the right direction. These can be laminated in different sections, and they have some added benefits that we don't get from the normal soft magnetic materials. And that would be a higher induction with a lower electrical conductivity, so we don't have as many eddy current problems, or that can be a higher or lower coercivity than some of the other soft magnetic. Some of the magnetic properties of nanocrystalline that you might notice that would make it advantageous as a core material versus a steel, laminated steel, or a ceramic material would be that the saturation induction is much higher than these ceramics. Some of the advantageous properties of nanocrystalline materials, they can be made in many different shapes to be cores inside motors, resolvers, transformers. And the properties that you might look for are a higher saturation induction than their ceramic counterparts. These would need to be laminated because they are electrically conductive, where the ceramic cores are not. So you have some eddy current problems if you don't laminate these, but that's not an issue for us. So we have a higher saturation induction, which has a higher density efficiency. We can push that at a higher magnetic field. We also can use higher frequencies than the ceramic materials due to the higher permeability of the nanocrystalline. It does have some differences versus the core-rolled steel. Crystalline material can be laminated very thin. It's used in a lot of shielding applications, such as wireless charging, to couple the coils together. This raises your charging efficiency by quite a bit. Previously, this was done with ceramic sheets or amorphous materials with lower saturation induction, which meant lower charging efficiencies, or it has no shielding at all, in which case you don't get good coupling. You don't get a good read between the two coils. It's also used in resolvers, filters, cores, things like that for filtering power. Maybe in EV drivetrain situations, you would need, if you have an AC induction motor especially, you would need some sort of filtering, or any sort of power inverter. You might use this in the transformer core or as a resolver filter.